In this discussion, we're going to talk about the function f of x equals e to the x. Particularly, we're going to focus on thinking about what is the derivative of this function. How do we differentiate e to the x? The thing is, though, that we haven't talked about this function since we started with derivatives. So in order to investigate this question, we're going to have to go back to first principles. In other words, we're going to have to go back to the limit definition of a derivative. In this discussion, I will use the limit formula involving h. So going back, we know that f prime of x, by definition, is equal to the limit as h approaches 0 of f of x plus h minus f of x divided by h. Then we're going to go ahead and do our substitutions. For example, I need to do f of x plus h. So we're going to take x plus h and substitute it into the function. So this is going to give us e to the x plus h minus f of x, which is e to the x over h. Then here, we're going to use properties of exponents or laws of exponents to re-express this as to powers. For example, this is what I mean. We're going to have the limit as h approaches 0, and we will rewrite this as e to the x times e to the h minus e to the x divided by h. And then, if you notice right here, I have a factor of e to the h, and here I have a term that has e to the x. So I have a common factor. That means that I can factor e to the x out. So this will give us the limit as h approaches 0 of e to the x times e to the h minus 1 divided by h. Now, a crucial step. We know by now that the variable that appears under the limit is really the variable that we need to focus on. What I mean by that is the following. Here I have h and x, but then h is really the variable that is being taken by the limit. E to the x is not. There's no h here. So then that means that I can take e to the x and place it in front of the limit notation. Like we do to coefficients, for instance. E to the x doesn't depend on h. So we can pull it outside. And we can rewrite this as e to the x times the limit as h approaches 0 of e to the h minus 1 divided by h. So again, e to the x doesn't depend on h. Here, I'm only going to leave the expression that fully depends on h. Anything else that has an x or something goes outside. So then, when I look at this, now my challenge is to figure out whether this limit tends to something finite, whether this limit exists. If I can figure that out, then I know how to proceed. Now, the thing is that we are not going to try to do this in any algebraic way because this would be really tedious. So then what I'm going to do is I'm going to try to convince you that this limit exists by looking at a table of values and looking at the graph of this expression. So right now, I will consider this as a function. Let me go here. I will think of this as y equals e to the h minus 1 divided by h. And I'm going to go ahead right here, if you notice. I'm going to pull this window out and we're going to focus on this information. Notice right here is the same function. This one right here appears here, e to the h minus 1 over h. I have already created a table of values with the focus around 0. I have some very small negative values to the left of 0 and very small positive values to the right of 0, right? If I am examining a limit around 0, then I choose small values really close to 0 from the left and from the right. Let's do the ones on the left, the negative ones. As my x values get closer and closer to 0, look at the y values. They're getting closer and closer to 1. In the positive direction, as my x values are getting closer and closer to 0, the y values are also getting closer and closer to 1. At 0, it shows as undefined. I don't care about that. I don't care what happens at 0. Remember, when we are analyzing limits, we don't care about what happens exactly at the value of the variable, in this case 0. We only care about what happens around it. So around it, we know that the y values are approaching 1. You can see it here. We can see it here. If we go to the graph, we see the same behavior. As x approaches 0 from the left or 0 from the right, look at the graph. The graph is approaching 1 on the left and 1 on the right as well. So I think that it is safe to conclude from all this over here that the limit as h approaches 0 of e to the h minus 1 over h is equal to 1. So now what I am going to do is I am going to take this discovery or this realization and use that information here. So going back to that, we're going to have that this is equal to e to the x times 1. This is the value of that limit, which is equal to e to the x. And how beautiful is that? Because what we just discovered here is that if f of x is equal to e to the x, then its derivative is the function itself. That's great. That makes working with this function super easy. E, it's a fantastic number for the reason that E can be complicated. Like, if you just think of E as a real number, we know that E is approximately, I think it's 2.71828, and then this number, which is irrational, continues forever. So it's complex. That's what I mean by E being complex. But at the same time, E can be rather simple if we view it as a function, because as a function, y equals e to the x, we just discovered that its derivative is itself. And this will make questions involving e to the x pretty easy to work with, especially with respect to differentiation. We're going to see exactly how to use this result in the next example. This question here is asking us to find the tangent line to the graph of f of x. F of x is equal to 3e to the x minus 5x squared at x equals 2. So we have to find the tangent line, the equation of the tangent line. In order to do that, that means that we're going to have to find the slope of the tangent line first. So let's differentiate. Let's find the derivative of f of x. So we're going to have that f prime of x is going to be equal to 3, this is a coefficient, nothing changes, times the derivative of e to the x. But we just found out that the derivative of e to the x is itself. So 3 times e to the x minus, and then over here we have a power term. So we're going to use the power rule. That means that this is going to give us 10x. Pretty simple. Now, in order to find the slope, I'm going to go ahead and compute f prime of 2. So then this is going to give us 3e squared minus 10 times 2, which is going to be 3e squared minus 20. So this is the slope of the tangent line. Now, in order to find the equation, I need the point of tangency. I know that the point of tangency happens at x equals 2, but I need the y value. So that's easy to find. I'm going to use the function. So when x is equal to 2, I'm going to find f of 2. And that is going to be 3e squared minus 5 times 2 squared. I am getting this from right here, the function itself. I am substituting 2 in place of x. So continue with simplification. This will give us here 3e squared minus 5 times 4, which is going to be 3e squared minus 20. So then that means that the point of tangency is going to be the point with x value of 2 and a y value of 3e squared minus 20. And the slope of this line is going to be f prime of 2, which we already know is 3e squared minus 20. So then, now that I have a point of tangency and the slope of the line, I can use my point slope form of a line to be able to find the equation. So then that's going to be equal to y minus, and then the y value of my point of tangency equals to the slope. The slope is 3e squared minus 20 times x minus the x value of the tangent of the tangent point, so x minus 2. And then all that I have to do is to isolate y by taking this term and bringing that term to the other side. So then I'm going to have y equals, then over here 3e squared minus 20 times x minus 2 plus 3e squared minus 20. And that becomes, right here, this is the equation of the tangent line. Okay. This is the equation of the tangent line at x equals